Good day. This is Bennett, also known as Jeremiah. Today we're going to focus on rates of reactions. The whole topic in under an hour. If you're interested in more videos, the playlist is found at the end of this video. It is also found right here on the top right of the screen and the suggested video. So, let's begin. Alright, let's start from the basics. So I'm going to use this to explain the basics. So, whenever, let's just say we've got a substitution reaction. So notice that we had A paired with X, now we have got B paired with X, right? So now this time A is paired with Y. So this is a substitution reaction. So let's just say we've got a reaction. So before a reaction happens, notice that this has to split. So they need to break. So this will split. So this will become AX, right? And then this will become BY. So notice that they have to split first before they can switch places, right? Before they can switch places and B can now pair with X and A can now pair with Y. So before they switch places, they need to break up first. And notice that these two are bonded together. So for it to break, there is a certain energy that is needed for it to break. So there is a specific amount of energy that is needed for these bonds to break so that we can have them splitted. This is why we have what we call activation energy. Activation energy is the minimum amount of energy that is needed for the reaction to take place. So in order for reaction to take place, they first need to split. So the energy that is needed to break that bond is called the activation energy. So that amount of energy that is needed for the reaction to take place is called the activation energy. So what activation energy does is that it splits the bond so that they can be in a state of activation complex. Activation complex is the intermediate state that occurs when reactants are being converted into products. So think of it as halfway between the reactants and products. So activation complex is when they're temporarily splitted. So they're temporarily splitted and they're in a high energy state. So I'm going to explain these definitions using the equation and also using the graph. So if we draw a graph of endothermic reaction, so let's say we've got something like this. So why is this endothermic? Notice that this portion is the energy of the reactant and this portion is the energy of the product. So whenever the energy of the product is higher than the energy of the reactant, this is called endothermic. So the reason it's called endothermic reaction is because it gained heat. So notice that the heat after is more than the heat before. And now notice that this part is actually called the activation energy. Why? Because notice that at this state, this was the energy level right before the reaction happened or before the bonds broke. So for us to break these bonds, we need to introduce a certain amount of energy. So when we introduce that energy, which is this space, that's when it is now temporarily separated. So this is activation complex. So the highest point in the graph is actually known as activation complex, right? So from the lowest point to the highest point of the graph is called activation complex, the highest point. However, this space between is called the activation energy. So this is energy that was added on top of what the reactants already had. So when we add that energy, it reaches activation complex. So I want you to understand that at this particular point, this is how the molecules look like. So they are temporarily separated. Now when they switch places, for them to bond again, it releases energy, right? So why does it have to release energy? Notice that the more kinetic energy the molecules have, the more they vibrate. So they won't be bonded to each other. So for it to be bonded, it has to release energy. So hence the energy now goes back down so that they can be bonded. So I want you to memorize that energy is gained for bonds to break and then they are released again for new bonds to form. So sometimes the energy that will be left will be more than the energy before. Sometimes the energy that is left will be lower than the energy before. So this is what makes it endo or exothermic. So if the energy it drops to is more than the energy it had before, then this is endo because endo means entry, so it gained energy. But if the energy is less than what it was before, then this is exo. Exo means exit, so it released energy. So if it releases energy, the energy will be lower than before. But if it gained energy, the energy will be higher than before. Let me redraw this graph and introduce some new things, then we'll attempt questions on this graph. Then afterwards we move on to another section of rates of reaction. Alright, let's just say we've got an endothermic reaction. So this is the energy of the reactants. And then now notice that this part, after the whole reaction has taken place, is actually the energy of the product, right? So this is energy of the product. So energy of the product. Now this space is called the activation energy, also known as EA. And then the highest point on the graph is called the activation complex, right? Activation complex. Now what I want you to know is that there's what you call the enthalpy, or the heat of the reaction. This is equals to the energy of the product minus the energy of the reactant. So it's this difference, this space, right? This space, the space between the energy of the reactants and the energy of the product. So this gap here is what you call the enthalpy. So this gap here is what you call delta H. Alright, let's attempt this speedily. So let's just say you're given this particular graph and you are told to mention the energy of the reactant. So if they ask which letter represents the energy of the reactant, so letter A represents the energy of the reactants, right? This portion. So the energy of the reactants is going to be 1200 joules. So if you ask for the energy of the product, well, the energy of the product is this portion. So that is going to be B. So that's how it is. So the energy of the product, so energy of the product is this portion, which is equivalent to 2000 joules. So 2000 joules. And then let's say you are asked for the activation complex. So activation complex is the highest point, right? So that energy is going to be 5000 joules. So it's supposed to be 5000. So 5000 joules. So that is going to be, so the activation complex is 5000 joules. So now let's say you ask for the enthalpy. What is the enthalpy? So the enthalpy, or the heat of the reaction, is always equals to the energy of the product minus the energy of the reactant, right? So the energy of the reactant. So now we just have to subtract. So we just have to say this portion minus this portion, right? So we just have to say this minus this. So the enthalpy, so we'll say the enthalpy is equals to the energy of the products minus the energy of the reactants. So that is gonna be, so we're gonna have 2000 minus 1.2. So we're gonna have 2000 minus 1200, which is gonna be 800. So 800 joules. So that is the heat of the reaction. So now let's say they ask for the activation energy. So what is activation energy? Activation energy is always this portion, right? So we're talking about from the energy of the reactants to the highest point. Even if the reaction is this way, so even if you have it like this, activation energy will always start from the energy of the reactants, right? So it will always start from the energy of the reactants to the highest point. So that is EA. So activation energy is represented by C in this case. So EA. So how do we get EA when we're given this type of graph? So we need to find this space. Notice that this side is 1.2, right? 1.2. So we have 1.2. And this side is the activation complex, which is 5000. So we just need to minus them. So we need to say 5000 minus 1.2. So EA is 5000 minus 1200. So that should be 3.8. So 3.8 joules. So that is the activation energy, right? The minimum amount of energy needed for the reaction to take place. And then let's say they ask you, is this an endothermic reaction or the exothermic reaction? There are two ways to explain it. So notice that whenever the energy of the product is higher than the energy of the reactants, energy has been gained, right? So the word endo means entry. So it's an endothermic reaction. If they ask us, is it endo or exo, we'll tell them it's endothermic, right? So we'll say it's endo because the energy of the product is higher than the energy of the reactants. So that is one of the ways. The other way to tell them that it's endo is you have to look at the enthalpy. So if the enthalpy is positive, right? So if the enthalpy is positive, greater than 0 means positive, right? Whenever you see A greater than 0, that's saying A is positive. And whenever you see A is less than 0, it means A is negative. So whenever the enthalpy is positive, it means energy has been gained, so it's endo. Whenever the enthalpy is negative, it means energy has been lost, so it's exo. So notice that enthalpy is energy of the products minus the energy of the reactants. So if the energy of the product is higher than the energy of the reactants, enthalpy will be positive. So it's endothermic. If the energy of the product is less than, so if EP was less than ER, so if we had, let's just say EP was, so let's just say energy of the product was 200, energy of the reactants was 500. Notice that when we get the enthalpy, right, it will be energy of the product minus energy of the reactants. So we'll end up having 200 minus 500. So notice that it will be minus 300. So the enthalpy will be negative. So whenever the enthalpy is negative, then it is an exothermic reaction. So there are two ways to tell them whether it's an endothermic reaction or whether it is an exothermic reaction. The first way is to compare the energy of the product and the energy of the reactants and tell them which one is bigger. The second way is to look at delta H, the enthalpy, whether it is positive or negative. So let's move forward. So if they give us this reaction and they ask us is it endothermic or exothermic, we'll tell them it's exothermic because delta H is negative. So it's as simple as that. All you have to do is to look at this stuff. Sometimes they actually tell you that delta H is equals to minus 1.2 joules, right? So sometimes they tell us that this is delta H. So by saying that it's negative, we already know that it's exo. If it is positive, the reaction is endo. Alright, let's talk about rate of reaction. First, let's define it. So the rate of reaction is the change in the amount of products per unit time. You can even say it's the change of amount of the reactants per unit time. If you want, instead of saying change in amount, you can say change in mass or change in concentration or change in volume. So it's up to you. Rate of reaction is represented by this formula. Rate of reaction is equals to change in concentration or change in mass or change in volume over time. Alright, let's just say we've got a particular reaction. So by looking at the graph, you should be able to tell whether a particular compound is a product or a reactant. For instance, if you see it increasing steadily, this is a product because products are being formed during time. So as they're being formed, they increase in either mass or concentration or volume or even number of moles. So whenever you see it increasing steadily until it becomes horizontal, this is a product. So the reaction comes into completion around this point. And if you see it steadily decreasing, you know that is the reactants because reactants get used up during the reaction. So around this particular point, that's when it comes into completion, when it becomes horizontal. Alright, let's do an example of how to answer it in past papers. Alright, let's look at this particular question. So it's taken from a past paper. So hydrogen peroxide decomposes and forms water and oxygen. And you're given a graph. Now notice that we know that this is the product because it is increasing, right? Products are being formed, so hence they have to be increasing in mass during time. So we know that this is a product because it is forming, right? It is increasing. So reactions decrease because they're getting used up and products increase because they're being formed in the reaction. So over time they become more and more. So here you're given that is the mass of oxygen, and as you can see, oxygen is part of the product. So this is the mass of oxygen being formed per unit time. So now before we look at the actual questions, I just want to introduce a question. So let's just say they ask you to find the rate of reaction during the first 3 to 9 seconds. So what you'll say is that the rate of reaction in this case, because remember rate of reaction can be change in concentration, or it can be the change in the mass, or it can be the change in the number of moles, or it can even be the change in the volume. So it depends on the situation. So in this particular situation, because we're given the mass, we will consider the mass, right? We'll say the change in mass over the change in time. So that's the rate of reaction. So we're told during the first 3 to 9 seconds, so 3 to 9 seconds. So we're just gonna say the bottom 9 minus 3, right? So change in mass, it's gonna be the final mass, right, of the 3 to 9 seconds minus the initial mass of the 3 to 9 seconds. So this is gonna be, notice that the final is 0.6, so we're gonna have 0.6 minus 0.4. So then this will become 0.2 over 6, which is equals to 0.03. Now what is the SI unit? Now notice that the SI unit depends on the situation as well. So notice that here, because we said mass over time, mass is in grams in chemistry, right? And even here, mass is in grams. So if it was not in grams, if it was in kgs, we would have used kgs, but usually mass is in grams in chemistry. So this mass is in grams, so it's going to be grams per second, because notice that it is mass over time. So grams per second. So if it was volume, volume would have been in decimeter cubed, so therefore we would have said decimeter cube per second. So for rate of reaction, it depends. You just have to take the SI unit of this stuff and the SI unit of this stuff. But it will always be per second, right? Because at the bottom, we will always have time. Hence, it's called rate. Every time we use a rate, it's always over time. Notice that also in physics, power is the rate of work being done. So notice rate, so work over time. So in this particular case, rate of reactions is grams per second, because mass is in grams and time is in seconds. So if it was volume, it would have been decimeter cube per second. If it was change in number of moles, let's say per unit time, we would have had it as the SI unit would have been moles per second, right? Because the SI unit for number of moles is moles. So that would have been the rate of reaction. So let me just erase this stuff. Just before I continue, if you want to be treated, whether it is online or physically, whether it is the situation where you're struggling in maths, or whether it is the situation where you're good in maths but want perfection, take a screenshot or save these details. Whether you're studying Cambridge, which is the UK curriculum, or whether you're studying NSC, which is the South African curriculum, or IEB, or native courses which start from N1 to N6, or any curriculum you're doing, no matter which country you're at, we offer tutorials. We've got lessons and practice sessions 5 days a week. We also give you tests once a week so that we can check your improvements. So now, let's look at the first question. So the first question says, write down. Every time they say write down, it means there is no, there's not a lot of thinking, there is neither a lot of calculations. So it's 1 mark. So now they said write down. So now they said write down the rate of production of oxygen gas for the interval 30 to 36 seconds. So from 30 to 36 seconds. So what I want you to notice is that rate of reaction is actually the gradient of the graph, the steepness of the graph. So the more steepness there is, the higher the rate of reaction. The more shallow it is, the less the rate of reaction. But now here it is straight, meaning that the gradient is 0. So therefore the rate of reaction is 0. So 0 grams per second. So now here they said, will the rate of reactions in the interval 3 to 9 seconds be greater or smaller or equals to the rate of reaction at 9 to 20 seconds? So they're basically comparing, they want you to compare 3 to 9 and 9 to 20. So they basically want you to compare this portion and this portion. So they're asking you, is this rate, is the rate from, notice that they said is the rate from 3 to 9 seconds greater than or smaller than or equals to the rate at the interval, right? The rate of reaction at the interval 9 to 20. So they're asking you, is this portion greater than or equals to or smaller than this portion? So notice that this portion is more steeper than this portion. So because of that, the rate of reaction from 3 to 9 seconds will be more than, right? It will be higher than the rate of reaction from 9 to 20 seconds. So you'll just say greater. So greater. So that's how it is. The steeper it is, the greater the rate of reaction. You must know that at the start, the rate of reaction is more than at the end, right? So at the beginning, reactions are happening faster, then they begin to slow down until it's finished. There's no more reaction. So notice that at this point here, the reaction reaches completion. So hence we've got the horizontal graph. There's no more reaction at that point. Alright, now let's look at this question. So now before we do this question, let me just give you a small revision of stoichiometry. Alright, here is the situation. This is taken from Level grade 11. So they said sulfuric acid reacts with ammonia to produce the fertilizer ammonium sulfate. So that basically saying that this reacts with this in order to produce this. So they said, what is the maximum mass of ammonium sulfate that can be obtained from 2 kg of sulfuric acid and 1 kg of ammonia? So whenever they ask you what is the maximum mass that can be produced, and they give you a certain amount of either mass or volume or concentration, what you have to do first is to look for the limiting reagent. So usually when we react 2 reactants, one of them will finish first, and once one of them finishes first, the reaction stops because the other one that is left has nothing to react with. For instance, if this finishes first, this one will have nothing to react with once this is finished. So when this finishes, their whole reaction stops. For instance, if this is the limiting reagent, then it means that if this finishes, the whole reaction stops because this will have nothing to react with. So once this finishes, the whole reaction stops. So how do we find out the one that is the limiting reagent? So they say 2 kg of this reacts with 1 kg of that. So now in chemistry, mass is in grams, while in physics, mass is in kgs. So what you have to do is to convert it to mass. In order to convert kgs to mass, you just have to multiply by 1000. So these 2 kgs becomes 2000 grams. So we're given 2000 grams. And then 1 kg becomes 1000 grams. So in order to find out which one will finish first, it's not necessarily by the amount of mass they have. So in order to find out which one is the limiting reagent, you have to find out which one will produce less product. So the one that will produce less product is the limiting reagent. So in order to find out which one will produce the lower amount of product, we have to strictly convert them into the number of moles. We cannot use the mass to discover that. We cannot use the concentration to discover that. So we have to get the number of moles. And the number of moles is going to be N is equals to small m over big M. So M is equals to small m over big M. So now we know that the mass, so the mass here is going to be, so first I'm going to calculate the number of moles of this, then I'll also calculate the number of moles of this. So the number of moles of the first one, the mass is 2000 grams, so we have to put it in grams. And then the molar mass, in order to get the molar mass, we have to look at the periodic table. So we want to get the molar mass of H2SO4. So in order to get the molar mass, we have to look at the periodic table. So we are looking for H2SO4. So in order to get the molar mass, what you have to do is to look at the atomic mass of each element. So the atomic mass is usually represented over here. So we're looking for hydrogen. So for hydrogen, notice that the molar mass is 1. So some periodic table says 1.01, some says 1. You'll use the one that is provided in the exam. So this specific one actually says 1.01. And there are 2 of them because of these 2 at the bottom. So we're going to have 2 times 1,01. So 2 times 1,01. So then there's going to be plus sulfur. So the molar mass of sulfur, so is sulfur, sulfur is here. So the molar mass is 32.1 according to this periodic table. So we'll say plus 32.1. And then we have to look for oxygen. So we know that oxygen is going to be 16. So oxygen is 16. So 16.0. So notice that there are 4 oxygens, right? So then we're going to have plus 4. So it's going to be plus 4 times 16. Alright, so let's type this in the calculator and let's find out what it gives us. So that will give us 98.12. So then we're going to say the molar mass is 98.12. Alright, so now let's find out the number of moles. So 2000 divided by 98.12. So that will be 20.38. And then the SI unit is moles. So now let's also calculate the number of moles of ammonia. So then we're going to say N is equals to small m over big M. So then this is going to be 1000 grams, right? Because this was 1000 grams. Alright, so there's no need to put the SI unit in the calculation. So we have to look for the molar mass. So now we want the molar mass of NH3. Now notice that it was actually 2NH3. However, you do not consider the molar ratio when you are calculating molar mass. So you do not say 2 times whatever is here. So let's ignore this 2 and let's just focus on the rest of the stuff. So we're looking for nitrogen. So where is nitrogen? So nitrogen is here. So 14.0. So that is the atomic mass. So the atomic mass is 14. So we're going to say 14. And then notice that there are 3 hydrogens. So it's going to be 3 times. So we already know the atomic mass of hydrogen, which is 1.01 according to this periodic table. So we're going to say 1,01. So then this is going to be 17.01. So the answer is 17.01, or rather 03. So it's 17.03. So now we're going to say 1000 divided by 17.03. Let's find out what does that give us. So that will be 58.72. So 58.72 moles. So how do we find out the one that will produce less product? You also don't look at the one with the lower number of moles. So in order to find out which one will produce the lower product, what you have to do is to, first of all, we want to find out how much product will each produce. So first we'll find out how much of this product can this produce. Then afterwards we'll find out how much of this product can this produce. So in order to find out how much of this will be produced by this, we have to compare the molar ratios. So H2SO4 and ammonium sulfate. So H2SO4, when you look at the molar ratio, there is an invisible 1 here, and here there is an invisible 1. So it's basically 1:1. So let me write it over here. So notice that it's 1:1, right? So this one is for this one, and this one is for this one. Now the method that I'm going to use here is simple, it's not hard. So now what we have to do is to write down the number of moles of each underneath these ratios. For instance, we know the number of moles of H2SO4, right? We calculated it, it was 20.38. Sometimes we have to calculate it, sometimes they give it to us. So what we'll put underneath this one, because this one belongs to this, is actually going to be 20.38. And then with this one, right, which belongs to this, do we know the number of moles? We do not know the number of moles. We don't know how much will this be produced by this. So that's what we're trying to find out. So because of that, we'll just say X. So 23.28 is to X. So we're still trying to find out this, so hence we put it as X. We do not know it. So from there, all you have to do is just to cross multiply, literally. So you're going to say X times 1, which is just X. And then from there, you're going to say equals to. And then from there, you're going to say 20.38 times 1. So that is still 20.38. So it means we found the value of X. So the value of X is just 20.38. So what then it means this will produce 20.38 moles of this, because they're the same, right? The molar ratio is 1:1, so that's why we have the same answer. Now let's find out how much of this will be produced by this one this time. So notice that the molar ratio is 2:1. So we'll just write 2:1. So underneath this, I have to write the molar ratio of this, right? So notice that this 2 belongs to ammonia. So the molar, the number of moles rather of ammonia is 58.72. So underneath this, I'm going to put 58.72. Then I'm going to say is 2. Then what is the molar ratio of this? Notice that this belongs to ammonium sulfate, right? It belongs to this part, and we do not know it, so I'm still going to put X. So in order to find out what X is equals to, I just have to cross multiply again. So I'm going to first start with this one. You can start with any, it's up to you. You can even start with this one first. So I'm first going to start with this one, then it's going to be 2X equals 2. Then afterwards, I'm going to multiply this stuff, so 58.72. So it means we're not done. We have to solve for X. So when you divide both sides by 2, we're going to end up getting 29.36. So that's what we have. So it means that, so I want you to notice that this one produces 20.38 moles of ammonium sulfate, while this one produces 29.36 moles of ammonium sulfate. So the one that produces the lower amount is the limiting reagent. So meaning that this is the limiting reagent, it means that this will finish first in the reaction. So once this finishes, the reaction stops. So in order to find out what is the maximum mass of this that can be produced from these two, we only have to use the limiting reagent, because once the limiting reagent finishes, the reaction stops. So we do not use the one that is in excess. So let's use this stuff. So far this produces 20.38 moles of this stuff. So we know that that's what will be produced by the limiting reagent. So we have the number of moles that will be produced from the limiting reagent, because this produces this number of moles, but this one produces this number of moles. So we strictly take the one from the limiting reagent, because once the limiting reagent is done, the reaction stops. So this one will not even be produced, even though it has the potential to be produced by this. So the number of moles of this that will be produced by the limiting reagent is 20.38. So from there, we have to find the mass that will be produced by the limiting reagent. So it's going to be M is equal to small m over big M. So then we're going to end up having 20.38. So we do not know the mass, that's what we're looking for. And then the molar mass, we have to use the periodic table. But we have already done it, so I'm just going to list them. So notice that the one for nitrogen was 14, right? And the one for hydrogen was 1.01. So it was 1.01. And then the one for sulfur was 32.1. And then the one for oxygen was 16. So now notice that we've got a slight problem. Here we've got brackets and we've got 2. So we do consider these 2. So what we have to do is that we have to say 2 times. So we have to put all of this in brackets. So the one for nitrogen was 14. And the one for hydrogen, notice that there is another 4 here. So it's going to be 4 times the one of hydrogen. So it's going to be 4 times 1,01. So notice that we had to put all this in brackets because there was a 2 at the bottom after this bracket. So meaning that all of this is twice. But if there was a 2 in front, we would not consider that 2. And then we have to say plus the one that belongs to sulfur. So sulfur is, the atomic mass of sulfur rather is 32.1, right? So sulfur. And then now oxygen, there are 4 of them. So we're going to say 4 times 16. So that's what we have. Alright, then from here we're going to end up having, so we can literally type this whole thing in the calculator, but let me just find it out. So this is going to end up being 4.04. So it's going to be 18.04. And then from here, we're going to end up having 64 plus 32.1. So I think that should be 96.1. So let's just add this in the calculator. So this should be 132.18. So this that we found was the monomass. Let's get back to the formula. So we said N is equals to M over M, right? And we got this before, it was 20.38. That's what we did, right? We said it was 20.38. And then we're looking for the mass. So the molar mass is 132.18. So now in order to make M the subject of the formula, we just have to cross multiply. So then this is gonna be M is equals to, right, when we multiply this stuff, it's just M. And this stuff, when we multiply them, this should be 2693.83. So this is in grams, so it's the same as saying 2.69 kgs. But let's just leave it in grams because mass in chemistry is in grams. So this is the maximum mass that can be produced. So stoichiometry is very important. It appears in this question and it also appears in chemical equilibrium. Alright, given that understanding, let's get to this question. So now they say the average rate of decomposition of hydrogen peroxide is this. So they gave us the average rate of reaction, right? Meaning that they gave us the whole reaction, the whole average of the reaction from here to here. But the problem that we have is that it is actually not for this graph. So the problem that we have is that we are given the rate of reaction of hydrogen peroxide, and yet this graph is not for hydrogen peroxide, it is instead for oxygen. So they gave us the rate of reaction of hydrogen peroxide, which is 2.1. So it's 2.1 times 10 to the power of minus 3, right? So notice that it's moles per second, meaning that here what makes it worse is that it's in the number of moles, it's not in mass. right? So it's moles per second. So moles per second. So then you can see definitely we're not talking about this graph, because this graph, first of all, we're talking about oxygen. Second of all, it's in mass, yet this reaction is in moles. So what are we going to do? So what I want you to notice is that we can use the rate of reaction of this stuff to find the rate of reaction of either this or this. So in other words, we are able to relate the rate of reaction, just like in stoichiometry. What do I mean? What I want you to notice first is that we are interested in the rate of reaction of this because we have got the graph, right? So we have the rate of reaction of this, but we want to find the rate of reaction of this. Notice that we can use the same method. Notice that the molar ratio is 2 and here's 1, right? So 2 is to 1. So now what I want you to notice is that the rate of reaction of this portion is given, right? Is 2.1 times 10 to the power of minus 3. The rate of this portion, which is what we want, is not given because that is what we're looking for. So this is very easy. Always remember that whenever you are given the rate of reaction of one compound, you can easily use it to find the rate of reaction of the other one. So what you will do is that you will just simply cross multiply again. So let's cross multiply. So this is going to be 2x and this is going to be 2,1 times 10 to the power of minus 3. So from here we have to solve for x, right? Because we want to get the exact rate of reaction. So when we divide by 2, our answer will end up being, so we're going to end up having x is equals to 1,05 times 10 to the power of 3. So now we have the rate of reaction of this one, right? So we now have the rate of reaction of oxygen. So when we have the rate of reaction of one, we can easily get the rate of reaction of the other. So notice that it is still in moles per second, right? It is not in grams per second. So what I want you to be aware is that this is in moles per second, but we have the graph of grams per second. So when you see this, notice that in the formula, I just want to show you something. Notice that if we were to write the formula, right, it would have been change in number of moles over the change in time, because this is moles per second. So now notice that we already have this portion, right? So it's 1,05 times 10 to the power of negative 3 is equals to. And notice that the whole time, the average time, is actually t minus 0. So it's just t. So the average time is t, right? Because this is the average rate of reaction. So we're given the time of the whole reaction, right? So we just have to say this minus 0. So notice that this is the change in the number of moles. So notice that the change in the number of moles is the same as the number of moles after minus the number of moles before. So we have to find the number of moles at this point minus the number of moles at the bottom, and the number of moles at the bottom will be 0. So for now, let me find this one. So now notice that n, the number of moles, is equals to small m over big M. So then this will end up being 0.9, right? We already know the mass and it's in grams, so we don't have to convert it, over the molar mass. So what is the molar mass of O2? Well, we already know that according to the periodic table, it should give us 16, right? So the atomic mass is going to be 16. So notice that there are 2 oxygens here. So therefore, we're going to have 2 times 16. So let's find out the number of moles. So this is going to be 0.028125. I don't want to round off because I'm not yet at the final answer. So notice that that is the number of moles, right? Now if we're to find the number of moles before, it's still going to be n is equals to small m over big M. But notice that the mass here is 0, right? So it's just going to give you 0 as the answer. So 0 divided by anything will give you 0. So it's still going to give you 0. So in other words, we're now going to have, so this part, okay, this part actually, the top part is going to give us this part minus 0, which is the same as this part, right? So it's going to be 0.028125. So all we have to do is to make t the subject of the formula. So if you want, we can use the long cut. The long cut is just to write it over 1 and then multiply, cross multiply. So then this is going to be t times, so let me just put numbers first before letters. So it's going to be 1,05 times 10 to the power of negative 3t, right? When you multiply this. So let me just write this in another place. So then this is going to be, so let me just erase this part. So now this is going to be 1,05 times 10 to the power of negative 3t, right? So that's what we get by multiplying this stuff. And then when you multiply this stuff, it's going to be 0.028125. So then from here, we just have to divide both sides by this, right? By this stuff. So then we'll easily get t. So it's going to be 1,05 times 10 to the power of 3. So let's find the answer. So therefore, t should be equals to 26.79. So that's what we have. Let's see if it makes sense according to the graph. Yes, it does make sense according to the graph, because notice it's after 20 seconds, right? And it's before 30 seconds. So it does make sense. And it looks like it's halfway. So that's how we know we're correct. So we must always make sense of the answer. Alright, let's move forward. Just before we proceed, if you're interested in knowing the prices of the tutorials, the video that contains the prices and the updated contact details, just in case these ones have changed, is found at the end of this video. Alright, let's talk about the collision theory. So, first of all, you have to know that all particles are moving, right? Whether in solid or liquid or gas. So particles are normally moving and they usually collide with each other, right? This might collide, this might collide. So they usually collide with each other. But now it's only effective collisions that can lead to a reaction. So what is an effective collision? There are two things that are required for a collision to be effective. Number one, they must be correctly orientated. So we're talking about correctly arranged. For instance, let's just say we've got this puzzle and we've got this puzzle. Notice that when they collide, they must fit. So number one, they must be correctly orientated. Number two, they must have enough kinetic energy. Whenever two particles collide, they need to collide with enough speed for a reaction to take place. So we need enough kinetic energy. So these are the two things that are needed for us to have an effective collision. Number one, they must be correctly orientated. So number two, they must have enough kinetic energy. Reactions are taking place. So think of rate of reaction as how fast reactions are taking place. There are 5 ways to increase the rate of reaction. Number one is the nature of reactants. Number two is to increase the concentration or pressure. Number 3 is to increase the temperature. Number 4 is to increase the surface area. Number 5 is to add a positive catalyst. So this must be known. Let me explain each of these. So let's talk about the nature of reactants. So what you have to be aware of is that the more reactive a compound is, the higher the reaction rate. So some compounds are more reactive than others. For instance, when we compare a weak acid and a strong acid, a strong acid dissociates completely in water, so meaning that substances are more reactive than others completely in water. For instance, however, weak acid does not dissociate completely, a weak acid does not dissociate completely. So some compounds are more reactive than others. Now for the following, I'm going to use this situation. Now most of us are more familiar with this thing that we find in an amusement park. Let's just say we're viewing this in the top view. So let's just say this is the pathway where they are driving the carts. Let's just say this is cat A, and let's just say this is cat B. Let's say this is C. Let's just say this is D. Let's just say E, somewhere here. Now, increasing the concentration is like increasing the number of carts. If I put more carts in this place, there will be more chances of collisions. So, increasing concentration increases the reaction rate. And let's talk about pressure. When we increase pressure, we are decreasing the volume. So picture it as though we're making the space smaller. So the smaller we make it, the more chances of collisions. So increasing pressure also increases the rate of reaction. Let's talk about temperature. When we increase the temperature, what temperature does to particles is that it increases their kinetic energy. So there will be more speed, more movement. So, if I increase the speed of each of these carts, there will be more chances of collisions. So, increasing temperature increases the reaction rate. And let's talk about surface area. This one is very important. For now, you can think of increasing the surface area as increasing the size of the car. So if I were to increase the size of the cars, there will be more chances of collisions. But one thing you need to know about surface area that they like comparing is that if we've got a solid, let's just say we've got a solid block. So first of all, you have to know that the more surface area, the higher the reaction rate. So I want you to be aware that this has got 6 surfaces so far, right? We've got 6 surfaces in this cube. But if I were to divide it into 2, notice that we will have something like this. As a result of it, more surfaces are exposed. So notice that we now have 2 new surfaces. So if I were to cut it again, we'll have another surface exposed. If I were to cut it again, we've got another surface exposed. So as a result, notice that if I were to cut it until it becomes small, so it will eventually become a powder. What you have to be aware of is that powder has got more surface area than solids. So if they compare a solid and a powder, we know that the solid has got more surface area. Now let's talk about the presence of a catalyst. So a positive, there is what you call a positive catalyst and a negative catalyst. But now most of the time they're talking about a positive catalyst. So a positive catalyst increases the reaction rate. How does it increase the reaction rate? So this is going to be very important to memorize. It lowers the activation energy. So a catalyst lowers the activation energy. Now let's just put it in this situation of cars. Now picture a person who is sitting and watching this guy driving. Now imagine this person directing this guy to bump this person. So this person is causing more collisions to happen. So this person is providing pathways for the collision to happen. So a catalyst increases pathways for reactions to take place. But most importantly, you have to memorize that the catalyst lowers the activation energy. So let's talk about the Boltzmann distribution. So this is very important. So it's something like this. So we're gonna have this stuff. So it usually has got this weird shape. So it has got this weird shape. So something like this. So what you have to understand is that here in this portion, we've got what we call the activation energy, right? We've got EA. So this represents particles, right? These actually are particles. So we have particles. Now what you have to understand is that particles in this portion have got more energy than the activation energy. So these are particles that are gonna have sufficient energy to react. So particles here will react. Now particles here have got not enough energy to react. So they are below the threshold, the activation energy. Now remember the 5 factors that increase the rate of reaction. One thing you have to know is that if concentration is increased, there will be more particles overall. So we will have something like this. So the size is just going to increase. Now notice that as a result, we will have a higher reaction rate because there will be more particles on this side as well. So you have to know how each of the factors increase the reaction rate. For instance, let's talk about the catalyst. What catalyst does is that it lowers the activation energy. So instead of the activation energy being here, if there is the catalyst, the activation energy will be somewhere here, for instance. So what this does is that it increases the reaction rate because now we've got more particles that have got enough energy to react. So this is just like lowering the pass mark. So if we lower the pass mark, more people will pass. Now let's talk about temperature. Now temperature increases the kinetic energy of particles. So meaning that more particles will be faster, so they will have enough energy to react. So what will happen to the graph is that we're gonna have something like this. So notice, so we're gonna have something like this. So notice that more particles will shift to the right because they've got enough energy. So the reaction rate increases. Now what about if we increase pressure? If we increase pressure, pressure has the same effect as increasing the concentration. So if we increase pressure, we increase the concentration. Alright, here is a past paper. So you are told that 3 experiments A, B, and C are carried out to investigate some of the factors that affect the decomposition rate, right? The rate of decomposition of hydrogen peroxide. Then they said the balance equation of the reaction is, so they gave you this stuff. So they said identical samples of hydrogen peroxide are used in each experiment. So now they said the conditions for each experiment are summarized in the table below. So at times they like giving you the table. So when they give you a table, you just have to compare them and see what is different. So notice that in experiment A and B, they've got the same temperature, but in C, the temperature has been increased. And we know that when the temperature increases, the reaction rate becomes higher. Now notice that here we have both these without a catalyst, but now here we've got a catalyst. So we know that when there is a catalyst, a positive catalyst, right? It increases the rate of reaction. So if you see them saying catalyst in past papers, they're talking about positive catalyst. So let's just look at the question. So they said, in which experiment A or B is the reaction rate higher? So let's look at experiment A and B. What is different in experiment A and B? Notice that they both have exactly the same temperature. Now experiment A is done without a catalyst, experiment B is done with a catalyst. So obviously experiment B will have a higher rate of reaction because catalyst increases the rate of reaction. So the temperatures are the same. So there we have it. So we know that it's gonna be B, right? So now let's look at 5.2. So now 5.2 says the Maxwell Bolt distribution curves X and Y for two of the above experiments are shown below. So without even looking at the experiments, by this shape, we already know that temperature increases the kinetic energy of the molecules. So most molecules will now shift to the right because they will have higher energy. So we already know by looking at this and this that what changed was temperature. Now look at what they said. So they said identify the curve X or Y that represents experiment C. So they're saying between X and Y, which one represents experiment C? So experiment C, let's look at experiment C. So remember, the temperatures were the same, but in experiment C, it had a higher temperature. And we already know that the higher temperature will never be X, right? Higher temperature increases the kinetic energy of the molecules, so most of them will shift to the right. So therefore, this is experiment C. So we're done. So there we have it. Alright, the information that I've provided in this video is sufficient for you to practice past papers and get most of the marks. However, there are some few questions that need extreme application of stoichiometry. So I'm going to make a video on this type of questions and it's going to be part of the playlist. I'll also make a video where we focus strictly on experiments. Alright, we have reached the end of this video. I have included a playlist of similar type of questions. If you enjoyed this video, please like the video and subscribe to my channel. Any questions you've got or any video you want me to create, please comment below. See you in the next video.